In this video, you're going to learn how to use the second derivative test to find relative extrema. This is not on a closed interval. This is just for a function with no restrictions. And so you want to title your notes second derivative test. This test is going to be a fourth way to find information. So there's 4 tests you know so far. It's going to be very easy to confuse these, so it's very important that you're listening careful here. Otherwise, you're going to miss out on some information. Let's do a quick recap of things we can do so far. If we have a closed interval, we know how to find the absolute extrema by finding the critical values and plugging them into the regular function. That's only if it's a closed interval. We also know how to find where relative extrema occur on a function using the first derivative test. The first derivative test involves plugging into the first derivative. Makes sense? We also know, this was the most recent video, we know where points of inflection occur. We can find that, and we can also determine concavity on the function. Notice this did not involve extrema, and this one involved plugging into the second derivative. So that test had to do with this information, your most recent video. We're now going to find a third way to find a max or min value, and that's going to be done using the second derivative information. So it makes sense that we'll be plugging into the second derivative. As always, our goal is to do this without a graph, only using second derivative info, and we want to know where relative max and min values occur, not absolute, just relative. Let's do a visual of why this works and how it works. So pause the video and sketch these 3 graphs. So in order for the second derivative test to work, we really need a flat spot on a function. So I drew 2 different cases here of a function that has when I say flat spot, I mean the tangent line is flat. Well, a tangent line is only going to be flat when the derivative is 0. We don't want to do this when the derivative doesn't exist. So not that, because that would be a case at like a sharp point or a cusp. The derivative doesn't exist here or here. First of all, we can't do it when there's a sharp point because there's no concavity here. So the second derivative is useless. And we don't want to do it here because it won't give us the information we need. So those are bad. Only whenever the first derivative is 0. So picture a graph that has a maximum and there's a flat spot. Picture being right at the flat spot. The only way for there to be a maximum and to have the first derivative being 0 is if it's concave down. There's no other way to do it. So if you have a maximum on a graph and you're at a flat spot, meaning the first derivative is 0, it's going to be concave down. Now picture yourself on a graph and you're at a minimum and the first derivative is 0. So you're at a momentary flat spot and there's a minimum on the graph. That's only going to work if it's concave up. Right here, this is just another way of looking at it. We're concave down here. We already know that if it's concave down, the second derivative is 0. Right here, the first derivative is less than 0. Here, the first derivative is 0. Here, the first derivative is 0 again. I'm concave up here, and the second derivative is greater than 0. So we have a min here and a max here. So if you're at a max or a min, and you know the concavity, then you can tell whether it's a max or a min. Right here, this is the second derivative test, the theorem. Okay, so make sure you write this down. Suppose f is continuous on the open interval ab and the derivative is 0. Again, we need it to be 0. It can't be, does not exist. This is what it says. If the second derivative is less than 0, meaning the second derivative is negative, that means it's concave down. And at that point, at that c value, there's a local maximum. C is just some x value in the interval AB. If the second derivative is positive, greater than 0, that means it's going to be concave up. We already know that. And if it's concave up, and for a moment we have a flat spot, it has to be a minimum. Just like if it's concave down and we're at the flat spot right here, that has to be the maximum. There's no other way. If you look at the visual, it makes sense. Also, make sure you title this. This is the second derivative test. This is the second derivative test theorem, THM theorem. One thing to be aware of is if you're at that spot where the first derivative is 0 and you find out that the second derivative is also 0, or that the second derivative doesn't exist, you can't make a conclusion about max or min values. You really need the second derivative to be a positive number or a negative number so you can decide if it's concave up or concave down. If you ran into something like this, you might want to consider using another test like the first derivative test. Let's do an example here. I'm going to do this example in real time with you so you can follow it easier and you're not just mindlessly copying it down here. So we want to find the local extrema of this 4th degree polynomial. So first of all, we need to find the flat spots. There's a lot of things you know how to do now, and it's very easy to confuse the things. What am I going to do? Why am I going to do it? How am I going to do it? Again, we need flat spots, and flat spots only occur when the first derivative equals 0. Again, if you reason out what you're doing, it's easier to remember everything. So we might as well find the first derivative. That would be 4x cubed minus 16x. Let's set this equal to 0. We're essentially finding the critical points. The only way that I could solve this is, let's see, I can factor a 4x out. I'll have 4x squared minus 4. That is a difference of 2 squares, x plus 2, x minus 2. And then I have x equals 0. I have x equals negative 2, and I have x equals positive 2. These are critical values. It's just instead of plugging them into f or f prime, we're going to plug them into the second derivative. So we know, this is very important you listen closely and understand this. We know that at 0, negative 2, and 2, the derivative is 0. So let me draw some random polynomial. You know the derivative is 0. It would look like this, or like this, or like this, or like this. You're at one of these points. These are where the max and min occur. You just don't know, is it a max or is it a min? So you know there's a max or min at 0, but right now we have no idea, is it a max or a min? You're going to plug it into the second derivative, because that'll tell you the concavity. And if you know the concavity, you'll know if it's a max or a min. So for example, if you plug it into the second derivative and you get a negative number, you know it's concave down. Well, if it's concave down, then there has to be a maximum. All right. Another thing is if you plug it into the second derivative and you get a positive output, then you know it's concave up. If it's concave up, there's a minimum. So that's how the first or the second derivative is going to give us the information. So, one second. All right, I just wanted to write this little blurb down here. At these spots, we're going to check the concavity. The key here is you're plugging these exact numbers in. You're very used to doing things like plotting your critical points and doing the intervals and picking a test value in between. We're not doing that anymore. We're checking right at these spots. No intervals needed. So this test is actually a little bit quicker than some of your other tests that you know. Well, in order to check concavity, we're going to plug them into the second derivative. So I should probably find the second derivative. My first derivative was right here, so let's get the second one. That would be 12x squared minus 16. So I'm going to check, is it concave up? Is it concave down at these points? So let's plug them in. I'm going to plug 0 in, so make sure you're writing this down. Again, you need the work here. That would be 12 times 0 minus 16. That would be negative 16. That is less than 0. So my second derivative is negative. So now think, okay, if my second derivative is negative, what does that mean? That means it's concave down. And if it's concave down, just look, there's a maximum right in front of you. That means max. Now let's try the next one. The second derivative at 2, I'm not really doing these in any order. I'm just kind of plugging them in. That will be 12 times 2 squared minus 16. That would be 4 squared. 2 squared is 4. 4 times 12 is 48 minus 16. I'm getting 32. 32 is positive. So think, my second derivative is positive. What does that mean again? It means it's concave up. If we have a graph that is concave up at a flat spot, there's a minimum at that flat spot. Last one, the second derivative at negative 2. So I have 12 times negative 2 squared. This is actually going to give me the same exact thing because 2 squared and negative 2 squared are the same thing. So my second derivative is positive. That means it's concave up. If it's concave up, there is a minimum there. So that means at 0, where's I think? At 0, there's a max. at -2, there is a min. Sorry, at 2, there's a min. At -2, there is also a min. And notice we did this without even knowing what the graph looked like. I have no idea what this thing looks like. I just know where my minimums occur. So make sure you have that written down. And here's your conclusion. The key here is justification. If you don't justify it, it's useless. All right? Just the statement's not enough. F of 0, that's basically just saying at 0, there's a local max. So you could say at 0, there's a local max, or you could say f of 0 is a local max. Here's the key. The second derivative is negative, and don't forget the and, the first derivative is 0 at the x value of 0. F of 2 is a local min because the second derivative at 2, notice I plugged 2 in, was greater than 0, and the first derivative at 2 was 0. And f of -2 is a local min because the second derivative at -2, notice I plugged a -2 and I didn't go around it, I went right at it, is greater than 0. And the first derivative at -2 was 0. Notation is key here. There's a lot of notation going on. All right, we'll practice this in class. And remember, you have a quiz on all these tests next week before Thanksgiving break. So make sure you took these carefully and you listened. See you soon.